we present SynShot, a novel method that leverages a synthetic prior for few-shot drivable head avatar inversion. Using just a few input images of a person shown on the left, SynShot creates a personalized 3D Gaussian avatar that can be rendered with novel viewpoints and unseen facial expressions, demonstrated on the right. Current monocular methods such as Insta, splatting avatar, and flash avatar are trained on a single video of a person, which makes them prone to overfitting to specific viewpoints and expressions. This limitation becomes evident in reenactment tasks, where novel expressions and viewpoints transferred from the source actor, shown on the left, reveal the method's difficulty in handling unseen facial expressions and camera angles, often resulting in numerous artifacts. One solution is to use multi-view datasets with tracked meshes to train a prior model on human appearance and motion, enhancing generalization in personalized avatar reconstruction. However, obtaining a sufficiently large and diverse dataset with accurate tracking is both time-consuming and expensive. Existing datasets, such as Nursamble, Multiface, and Facescape, are limited in size, diversity, and realism, particularly in capturing in-the-wild appearances, as they lack important features such as hair. To tackle these challenges, we propose using synthetic data to train a dynamic human head appearance prior based on 3D Gaussians. Synthetic data offers scalable diversity and size, saving time and costs compared to traditional capture studios. In our experiments, we generated a synthetic dataset of approximately 2,000 diverse subjects, featuring a wide range of expressions, hairstyles, and identities. Using this dataset, we train our prior network, which takes as input position maps, texture maps, and expression deltas from a neutral mesh, and outputs a controllable three-dimensional Gaussian avatar. SynShot's architecture consists of a VQ-VAE component and lightweight Gaussian map regressors, which generate dedicated maps with Gaussian primitives for each facial part, such as hair, face, or beard. Our dynamic prior feeds facial expression, color, and position maps into VQ-VAE encoders, which map them to a quantized latent space and decode them into feature maps. To generate the final avatar, we use lightweight regressors that, based on the intermediate feature maps, predict the 3D Gaussian primitives, which can then be splatted to an image. Our human appearance prior allows us to change both the identity and facial expressions. Here, we demonstrate traversals for identity and expression by linearly interpolating latent codes between test identities, showcasing a smooth latent manifold. Inversion is the process of projecting images onto the latent manifold. Our inversion process is divided into two stages, similar to pivotal fine-tuning. In the first stage, we fine-tune our identity encoder to achieve the closest latent space projection of the in-the-wild avatar. Since this stage outputs an avatar with a synthetic appearance, stage 2 follows. In stage 2, we keep the latent codes fixed and fine-tune the remaining decoders and regressors to bridge the domain gap between the synthetic and real appearance and address out-of-distribution illumination, identity, teeth, and hair. With this scheme, we are able to reconstruct high-quality avatars that are leveraging the synthetic prior with all its diversity. We compare our method with the three state-of-the-art monocular methods, Insta, Flash Avatar, and Splatting Avatar. For our method, all experiments were conducted using only 3 input images, unless explicitly stated otherwise. As mentioned earlier, all baselines perform reasonably on the test sequences. However, many of these are in-the-wild videos with very limited head motion. Consequently, the test sequences closely resemble the training data, resulting in low error rates but limiting the assessment of diversity. To address this and accurately assess generalization, we conduct extensive reenactment tests and evaluate the quality of each method based on the number of frames used for training. In our reenactment experiments, we transfer the camera and expressions from the source to each avatar. As stated, all methods struggle and underperform with novel views and expressions producing artifacts, especially for the mouth interior, teeth, and eyes. Our method, which only uses 3 input images, significantly outperforms the baselines in generating novel views, maintaining expression consistency, and producing significantly fewer artifacts for the mouth and teeth, demonstrating the importance of a synthetic prior for generalization. We also provide an extensive qualitative evaluation based on the number of frames used to train each avatar, with the frame count indicated on the left. As shown, SynShot is flexible with varying input frame numbers, leading to improved quality. In contrast, the baselines struggle in both low and high input scenarios, especially for novel view synthesis producing severe artifacts. Additional examples are provided at the end of the video. Thank you for watching. We now present additional examples.